If you like the content of this video, please do press the like button and subscribe. We begin by studying the standard form of a second-order, ordinary differential equation. It is linear in y, and its derivatives p, q, and r are any functions of x. And as before, if the right-hand side is 0, we call it a homogeneous equation. We now consider the case where the coefficients of the ODE are constant. Choose e to the power lambda x as a solution and substitute in the homogeneous ODE. The quadratic equation will yield 2 roots for lambda. The linear combination of each of the solutions corresponding to lambda is also a solution. The proof is simple. This is called the superposition, or the linearity principle, and is true only for linear homogeneous ODE. The arbitrary constants, C1 and C2, are determined from the initial conditions. Y1 and Y2 are linearly independent and are called the basis of solutions. A particular solution is obtained if we assign specific values to C1 and C2. If Y1 is a basis solution, we can find Y2 using the technique of reduction of order. Choose Y2 as u times Y1, where u is a function of x. Compute the derivatives of Y2 and substitute in the ODE. Let u prime be capital U. We then solve for capital U. We then integrate capital U to get u, and then compute Y2 as uy1. For the quadratic equation, we have 3 cases: distinct roots, repeated roots, and complex roots. For repeated roots, to find the second basis solution, we use the method of reduction of order that we just studied. We can expand a function as a power series about a. The coefficients of the power series can be easily expressed in terms of the function and its derivatives evaluated at a. Then the Taylor series can be expressed as shown here. The Maclaurin series is an expansion of the function about 0. To expand a function as a Taylor series, we need to ensure that it converges. For convergence, we can approximate the sum as accurately as we want by taking a large enough n. We now define an important term called analytic function. A function is called analytic at a point x0 if it can be represented by a power series in powers of x minus x0 with a positive radius of convergence, r. For complex roots, we leverage our knowledge of Taylor and Maclaurin series to find the general solution. The Euler-Cauchy equation is shown here. To solve this equation, we set y equal to x to the power m. This reduces the problem to finding the roots of a quadratic equation, which can be real, distinct, repeated, and complex conjugate. We first express the equation in its standard form. For repeated roots, we use the same technique, the method of reduction of order, to determine the second basis solution. For complex conjugate roots, we can express the solution in terms of sine and cosine, using Euler's formula. We now establish the uniqueness of solutions in terms of the Wronskian, or the Wronski determinant. We have seen techniques for finding solutions to the homogeneous equation. The table here lists choices of functions for finding particular solutions. We Now establish a formal method for determining the particular solution. If y1 and y2 are known solutions to the homogeneous equation, we define a particular solution in terms of two functions u1, u2, and y1, y2, and enforce the constraint of equation 1. Compute the derivatives of the particular solution and substitute in the ODE to arrive at equation 2. Solve the equations 1 and 2 to find u1 prime and u2 prime. Integrate to find u1 and u2. We can now compute yp